today we will start a new topic, which I should actually discuss before the one last time, but I'll change the order intentionally so that we get a little bit understanding about the analysis procedures and then come back to the gravity load system and behavior. The main thing, there are a couple of things that I want to focus on. How does the load, so we've been talking about earthquake and lateral loads and wind, but we haven't talked about the mechanism in which the gravity load transfers through the floors to the foundation, because there's been a lot of development in this area and understanding this one. And people have gone through very simple to now very complicated understanding of this behavior. So first of all, primarily there are two parts: direct path system and indirect multi-path system. So direct path system is that you apply the load to the floor and it directly goes to the columns, and there is no long system. For example, flat plate, there is only one element, slab, which is the plate, and then there's columns. So you apply the load and it goes straight to the columns. But if you have, for example, a beam joist system, then I will show you later, then it's a multiple path, step by step. Okay? But understanding of this was a little bit mistaken earlier. People thought that they can guide the load in the way that they want, but we found later that that's not really true. The load will go how it wants to go, not the way that we want it to go. Okay. So that's the things that we will discuss today. So these are the direct load transfer system: flat slab, flat plate, beam slab, waffle slab, wall joint, indirect beam. Now please note this one. This is called beam dash slab. And there is another word called beam comma slab. It's not a mistype, or it's not that I sort of, it is very intentional. One is a dash and one is a comma. So when you put dash, combine two things together, you are supposed to read it as one term or one word, which means it works together. When you put comma, it is two separate things, but you're talking about as a group. Okay? So this is exactly what is happening in load transfer mechanism. One is a combined system, it works together, and one is a system that works step by step or one another. So this comma and dash is very important. So we have a beam dash slab system, and we have beam comma slab, girder comma beam comma slab, or girder and joist, these systems. Okay. This is the steps taken by the assumed load transfer mechanism. Okay. So we will go through these today. Let's look at this one now. This is a slab supported on walls. All four sides are walls, not beams, walls. Masonry walls, concrete walls, and this is slab. So the assumption is that the load will be transferred to each wall based on this triangle trapezoid rule. So this is what people have been thinking or have been using in the past, or still some people use it, to determine how much load will go to each support. So this triangle portion will go to that. This trapezoid portion will go to that. And we just draw a 45-degree line at the corner, extend them where they meet. So based on the geometry, we can determine how the load will be transferred, because that's the assumption that this portion belongs to this one, this portion belongs to this one. And this is the traditional way, and it still will work in this case. This is a second case now, where we have four columns, nothing else. So now we divide the space like this, because there's no support here. So we divide the panel into four parts, dividing each side by two, connecting them together. And we say this load will go there, this load will go there, this load will go there, this load will go. Right? This is called tributary area method, both of them. The tributary area supported by a wall or a support is supposed to get that load in that area, which is supposed to belong to it. Okay? So this is fine too. Now we have interesting combination. We have beams here, not wall, and we have columns which are supporting the beams. And now we don't know whether this or this will work, right? The assumption has been that that will work. So people say this load will transfer to the beam, and then beam will then transfer it to the column. This load will go to the beam and then go to the column, right? This is the assumption based on this analogy because we think that the beam is a support. Now, if the beam is very small, just equal to the slab, a little bit bigger than the slab, do you think it will still work? Okay, let's discuss this further. Another question. Now we divide this panel into two panels by putting a beam on this one, which means that now the load transfer geometrically should be looking like this, based on that previous slide, that this portion should now go to beam will take the wall, this portion will go to the wall, and so on. So by adding the beam, we have divided into two panels, and we are assuming that based on the geometry, the tributary area will be trapezoid triangle rule once again. Right? And that's what we have been doing, and people have been doing, and people still do. And then same thing, if we divide further this panel into two beams, and then we have four panels now. So we think that this panel will go to here, this will go here, this will go there, this will go here, then go here, go. So we are now assuming that this panel will split like this, go here, and then go back here, correct? And then if you have panels like this, then we're assuming this will go here, then go there, and go there. Okay. This is all based on the concept of the geometric location of the supports, assumed supports, and the slab system. But we will soon realize that this is not how the structure will work. It doesn't work this way. The loads are not transferred in this way. Okay? And let's see why not. To complete the discussion, if the load is applied directly to a structure as a point load, it has no other possibility than to go through that structure directly to the foundation. So you can just make this reaction to be equal to that load. So there's no load transfer and the column in between. If the load is applied to a frame like this, then we will assume that this load will go to each column based on the distance proportion. If this is closer here, this column will receive more load. When it's closer here, this column will receive more load. So this is something that you can calculate by hand, by simple, A over L concept. So this is A, this is L. So based on that ratio, you can determine, right? It's easy, simple as that. If it is a slab, it's a point load, and you assume the slab to be rigid and the columns to be flexible, or just assume that way, you can do the same thing. You can do 2A, 2 over 2Ls, and you can distribute, you can calculate the load in all the four columns based on their location from each edge and divide that by that. Right? This is the assumption that we use for when we have a column on a pile group and things like that. So people use this basic assumption of geometry, distance, to find the equilibrium and find the loads. And whether this slab is thin or thick, beam is big or small, it doesn't matter. Because that's the geometry, right? And when it's a solid medium, we also assume the same way as this one, that the load will go to the four corners as if it is a slab. So there's no difference between a completely solid block and a slab, or a very thin slab or a very thick slab. Our load transfer to the column, to the foundation, will exactly be the same. Which obviously should not be the case, right? Okay, let's go to next step. Now, this was the assumption that the loads will go like that, which we said that it's okay for a wall, and because there is no other mechanism possible to exist, so load must go like this. Okay. This one, we decided that loads will go like this. Once again, there is no other possibility but for the load to go here, because there is no other mechanisms possible. There is only direct load transfer. So there is no confusion. So this is correct, and we can't argue on this. However, we can argue now a lot here, because we don't know where would the load like to go. A load may want to go like this one, straight to the column, or load may want to go like that to the beam and then to the column. Correct? Because both are possible. Right in front of you, both situations exist. This situation also exists, And that distribution also exists. Now the question is, which one will be true? Yes.
Depends on the stiffness.
Correct. So now let's see, depends on the stiffness of what? Slab and beams. Correct. Slab and beam stiffness will decide out of the way these two, which path will exist, or how much percentage going straight, how much percentage going through the beam back to the column. Right? So which means now we have to consider the dimensions and the stiffness and the connectivity and the structural model before we can decide the load distribution mechanism. And that's lesson, the most important lesson. And we will go on a little bit further on this one. So this is, we have taken it from ETABS manual from a while ago, not now, ETABS 9, now it's 22, a long time ago. So ETABS 9, or at that point, the program did not have the ability to determine the load transfer mechanism through stiffness because it did not model the floor slab by any element. It assumed it to be a kind of a diaphragm, just something that exists but did not participate in the analysis because the computers were not big enough, it's not fast enough. So there was no way for them to create a model of the floor. So floor was assumed to be like a table, just resting on the columns, but it didn't participate in the stiffness distribution or calculation. Only lateral loads were considered and the frame was considered. Slab was not part of the analysis. So there was no way for ETABS to determine how to calculate the beam load and the column load. So they had this manual where they showed many diagrams, what is the internal mechanism they're using to compute. So the programmers wrote all those hundreds of cases, for each case, handwritten formulas on how to transfer the load. It was so much work and still can miss some cases. So this is from there. So you see here, there's a line load, it will go like that, and then it just goes on and on. And this one, like this one, this point load will go this way. Just because it happens to be here, it will go there. They just assume like that, something like that. So they just use based on the geometry, transfer beams over, it doesn't matter. There's no beam here, it will go like that. One beam missing here, it will go like that. So it was a very simplistic approach, like this one, it will go like that, and so on. So this was in that two walls will go like that, which is probably correct. And one wall, of course, cantilever will go like that. So they created all these hundreds of cases of load transfer mechanism, and it only worked for rectangular or mostly rectangular slabs. For irregular shapes, it was not easy to do those calculations. This was earlier. And so that's what CSI did. They said, okay, we can't do this for the whole building, but you can buy another program called SAFE. And it says SAFE will model one floor completely at a time. And there you can mesh it, and there you can use finite element, and there you can do the load transfer. So they said, okay, you want to design the floor, use SAFE to design the beams. And when it comes to the building, we will use this approach just to get the loads onto the column and do the lateral load and the mass correctly. But it won't design the floor or the beams. So beam design and floor design was left to another program, and frame analysis or the building analysis was left to another program. And then people used to transfer the data from one to the other. There's a lot of it. Last 3, 4, 5 years, 6 years ago, they brought the SAFE back into ETABS. So every floor is now in ETABS model. In ETABS, every floor is a SAFE model, so to speak. So it's a complete analysis design can be done within the program because now we have enough fast computers and memory. Okay, so all this information is now redundant, but still important to understand how the geometry load transfer works. There are more cases like that. It's still a good, way to understand how the load geometrically would transfer. Now let's come to the analytical approach when we can mesh the slabs and figure out now what is really going to happen to a floor transfer system. So now we have created those models that I showed you earlier in ETABS. So these are walls, red walls and wall, that's a slab. So the first one is all walls with a slab on it. Second one is we put 3 beams on this one. But what we did was the beam size is different in each case. Slab is the same, load is the same, lengths are the same. Here, this beam is larger, those 2 beams are smaller. These are larger beams, these are smaller beams. So in one, we could just put very small beams. In one, we put very large beams. And in one, we put 1 large and 2 small beams. So geometry-wise, there shouldn't be any difference. All beams should get the same loading, same bending moment, because the spacing is the same. In the plan, they will all look the same, right? And this was a big challenge when I started practice long time ago. We used to get these houses to design, and mostly they are based on slab supported on walls. But sometimes the architects want some wall to be removed, and there's a wall above that, so you need to put a small beam there. And beam cannot be seen because they don't want to see in the room, so beam has to be hidden. So it's a small beam. So our misunderstanding at that time was that this small beam, which is typically inverted, will carry the entire load. So we will transfer all the load to that beam because we don't know better. We don't have the tools. The load will become very large. The beam is very small. The reinforcement will become huge. And everybody will complain. The client will complain, the contractor, why are you putting 20 bars in this small beam? Because that's the moment that I got from my assumption. And then the funny thing is that there will be cracks into the beam because we thought that beam was a support. So we will stop the positive reinforcement and put the negative reinforcement like a wall over there. But actually the whole floor will deform, right? So this is what we will see here. So this is the simplified portion of the slab alone, slab with big, small, and then these are the results. So in deformation, you can see all of the beams are deforming with the slab. Beams are not helping at all. Even if we put the beams there, the slab is just still deforming as one panel. So the beams, just because we put the beams here, didn't do anything. They just deform with the slab because the stiffness is too small. So which means that we should not carry any loads to the beam. They're just a little bit stiffness, but they're not carrying any significant load. So they should not be designed for the slab load. They should be designed for their own load, plus maybe a little bit more, but nothing significant. And if that is the case, it will be perfectly fine. And here you can see here that the deformations now are different in each. This is less deformation here. This is stiffer. This is more deformation. And down the bending moment is the key that you can see from here. The bending moment for the same load, for the same spacing of beams is very, very small because they didn't attract any load. So the total load carried by the beams is really small. The bending moment is so small, as you can see here, right? Here, these 2 beams carry very little load. This beam carried a lot of load, even though the slab supported distance is the same. So if you use the tributary area trapezoid, you should get the same load and same bending moment in all 3 beams. But we didn't get it. We get very different moment in this one. And when we make all the beam bigger, they all got large moment. This will be compatible with the size of the beam. So when the reinforcement I design will not be too much because I have a lot of depth. So the bending moment is large, but the depth is also large. So I will end up with a small reinforcement. But if I assume that all beams are carrying moment like this and the size is like this, I would be over designing the beams for the load that they will never carry or don't have the ability to carry. So this slide should make us very clear that the load is not carried through geometry, but by stiffness. And the stiffness ratio between the slab and the beam is the deciding factor on how much load the beam will actually carry, not just because you put a beam there. You have to see what is the ratio of that stiffness of that beam to the stiffness of the slab that it's supporting. And this is a beam-slab system. This is a beam, slab system, right? So you can see the difference. Because here, beams are just part of the slab. They're not separate from it. And this is more clearly, you can see how clearly the moments are varying in each one of them. So, importance of stiffness. The load is carried by a combination of beam and slab based on the relative stiffness of the slab and the beam. That's the main lesson. and the slabs can be assumed to be resting on beam unless the beam stiffness is very large. How large do you think the stiffness of the beam should be compared to the slab that it is supporting before it is assumed to be a support or a beam, real beam? The stiffness of slab can be calculated B over T cubed by 12, and the stiffness of the beam can be calculated by section, B of the beam by H cubed over 12. So it's easy to calculate the I. So what should be the ratio, in your opinion, between the beam and the slab for the beam to be justified as a support? 5 or more. 5, 4, 4.5, 5, 6, above 5, it will start to be stiff enough to carry the slab and become a support. And that's the division used by ACI. After several studies, they have concluded that roughly the 5 is the limit, where before that you call it beam dash slab, and after that you call it beam comma slab. But again, 5 is, every limit is arbitrary. What about 4.9? What about 4.7? So it's a smooth transition, but roughly 5 above, you can start thinking it as a support. Below 5, it is not really a support, and it should be designed as part of the. So I'm talking about the stiffness ratio of the beam and the slab that it's supporting. So if I can draw it here, that is the equation, simple one. So you calculate the stiffness of the slab and calculate the stiffness of the beam portion, the web portion, and then you calculate the ratio. And this ratio is more than 5, which means the beam is strong enough to be called a support, something like that. Okay, so let's continue now to a tall building or a flat slab or a slab system. We just got the concept from a simple slab, but let's extend that into a real floor system and study what happens to this floor system when we introduced beams, or we don't introduce beams, or we increase the beam size, or we have flat. All different systems we will study now. So this is a slab. Let's say it's a typical building slab, 6 meters by 6 meters. It's not a big span, small span, but let's start with this one. If that is the model, then I'm using now flat slab here. I'm using slightly bigger beam here, quite small. I'm using a deeper beam and a very deep beam at the top. And we want to study how the bending moments in the beam and slab will vary with changing the height of the slab. So the ratio of the slab beam to slab thickness is not vary. This is about 5 or plus. This is 3. This is about 2, 1.5 or something. And this is was 1, okay, because there's no beam there. So using these, we can now analyze this structure and see what do we get. So we create the model here, and you can see it is real easily vertically the difference between very large moment in the beam, small moment, almost negligible moment, because we put the beam of the same size as the slab just to make the comparison, right? So which means it's clearly that the bending moment in the beam and correspondingly bending moment in the column will be different. Okay? So the problem is that no one will allow you to do that in reality. This deep beam, you will not, architects or clients, and nobody will allow you to put a beam which has a stiffness of 5 or more compared to the slab in a building, which means almost all buildings, real buildings, are beam dash slab. Almost none of them are the one where beam can be taken as a support, or where the geometric load distribution can work. So which basically means that before this knowledge came into clarity, we had no choice, but we were doing it incorrectly. And there were many consequences of that, mostly in cracking of the slab system and in over designing of the beams unnecessarily. Deflection was too high. So many things were happening at that time. So now that we have all this knowledge, we should consider this as part of, and the ACI was the first code to recognize that. Other building codes followed much later. So they recognized this somewhere in 1970 or 72 or whenever the computers start to come in and they start to do something like this, they start to realize and they introduce a process for that, which I will talk about, which is still used today. So we do this one, and now you can also see what is happening to the slab. So we have seen what happened to the beam. And this is a very important slide and slides that are coming through. Please try to understand what is this slide first, because it's too many colors. Let me explain to you what's happening. So the same slab that I showed you earlier, this one, now I'm trying to show you the bending moment in the slab portion. Bending moment in the beam is clear, but what is the bending moment in the slab itself, right? That's what we are looking at now through these slides. So this is the column is here where you can see red. Red means it's a negative moment in the slab, and green or blue means it's a positive moment. Positive moment means that the slab is bending like this. Negative moment is that it's over the column, the curvature is reversed. So if it's a negative moment, that means there is a support underneath that. That's why there is a negative moment. So whenever there's a red color, indicates that there is a support underneath that. And whenever there is a blue color, that means the maximum reflection is maximum, moment is maximum, there's nothing there. Now, if you observe this one, this is small beam or low beam. You can see that the red color only exists on the column, which means the beams did nothing. They did not represent themselves as a support. There is no negative moment developing over the beams. They just are still green and blue. They just deformed and they have the positive moment just like the slab. They didn't do anything. As we increase the beam size, then this red portion becomes bigger. This is the red portion now in the beam is becoming bigger. That means beam has started to be a support now, right? It has started to attract moment in the slab over the beam. And here, all of it now is, this is a medium, this is a very large beam. So almost all beam, all moment is now, slab is over the beam. And you will question why there is no negative moment in the slab over the column. And the reason is that all load has been transferred to the beam, and beam has taken all the negative moment. So slab doesn't have any negative moment left to carry because all load gone to the beams and carried to the columns through the beams, not to the slab. So slab is not resting on the columns anymore. Slab is resting on the beams, and beams are resting on the column. True beam, slab, beam behavior. So this is true with very deep beam. So this is and this is the medium one where it's well distributed on the beam and the column, right? So the whole line of beam and column acting as a support. So this observation tells us that there is a gradual transition from fully positive moment here to a fully negative moment here over the beam. And this is a mistake that we all made. Because if I put a small beam there, I thought I'm doing that. So I thought there will be no positive moment in the slab. So I stopped the slab bars. I didn't put any positive reinforcement bars in the slab because I think beam is going to carry that. But in reality, the positive moment in the slab will come. It will find no reinforcement there. It will crack. And then the beam reinforcement may help because it's also the same location. So this whole thing, gradually people start to understand, and now most people should know that this is how things are happening. And today also you know. Did you know that before? You're all graduate engineers. So if you didn't come to AIT and you go to a design office and start practicing design, you would be making the same mistake that I made 40 years ago. So it's not good that we haven't learned that much. Okay. And the other direction, the same thing. So this is another interesting observation, that the load is transferred in two directions simultaneously. Once in this direction and once in this direction. Okay. So the same, because of the two-way action of the slab system, load is always transferred twice. Same load goes 2 times, not half hour. Okay. This is another big misunderstanding that people have. I told you the story about when I joined the office and I want to design a flat slab. I had a big argument with our chief engineer because I was designing the slab like this. So first I designed the slab to carry the load in this direction. And then I designed the slab to carry the load in that direction. And he said, you are designing the slab twice for the same load. And I said, you are doing the same thing. You just don't know it because you are transferring once all the load to the beam, and then you're designing the beams to carry all that load again to the column. So you're also carrying the load twice before it reaches the column, but you just don't see it that way because once you think I'm doing the slab, once you think I'm doing the beam. But in reality, both of them are working as a system. So here, that is correct. The load is being transferred here and there, and here and there. It's a two-step transfer. Here's a single-step transfer in both directions. So it's very important to note that when you design floor systems, you have to carry the entire load twice, not half this way and half that way. All the load will be carried in two directions because it's a two-way system. It is supposed to be carried in two directions. So please do not get this misconception that we have to only carry half the load in this direction, half the load. Yeah, if you're doing a slab, yes, you will carry half the load to this beam, half the load to that beam, but then beam will carry that load back to the column. But here we are transferring the load directly to the column, so it must be full load in one step. So that is the plot of the bending moment in the beam. Once again, to show you on the plan how the bending moment in the beam varies so much, right? So this figure combined with this figure, these figures should give you a complete understanding of how this slab system works. And when you design the post-tension slab, same thing happens. You put the tendons to carry the load in one direction. We call bended tendons. And then you put the tendons in the other direction to transfer the load to these bands. So bands act like beams and then transfer tendons from there to here. So even post-tension slabs, we do post-tensioning twice in each direction, right? In one direction, it acts like a support. In one direction, it acts like a slab onto the post-tensioning. So post-tensioning is like a hidden beam that we create inside the slab. But post-tensioning, remember, we convert a two-way slab system into a one-way slab system. On one direction, we put the bands to carry 100% of the load. And then slab on the other direction, because there are no beams, so we can decide how the load will be transferred now, depending on the distribution of the tendons. So we design the tendons in such a way that one side of the slab, without having a beam, becomes a support. Because we have the ability now to control the uplift and the forces in the slab to create a situation where it does not deflect. Because what is the criteria here? Deflection. The load is transferred over the wall because the wall does not deflect. Load is transferred over a deep beam because it does not deflect. If it's a shallow beam, it deflects. So if through post-tensioning, we can ensure that slab will not deflect in one direction, we can create an artificial support and the slab will then go over it. Because in post-tensioning, you can post-tension in such a way that you lift up the slab to become straight. No deflection. Anyway, so that's the summary of this discussion. Stepping back a little bit, simplified design of beams and slab, one-way slabs, also can be used for post-tensioning. Because as I mentioned to you, we can convert the post-tensioning into one-way system. One's this way, one's that way. So this is the interesting part here. These are the what is called moment coefficients, right? You understand that, right? So this is supposed to be multiplied to, W L square and divided by this factor or multiplied by this factor. This will give you the moment here. Because important thing for you to remember here is what is the moment here? For a UDLW and span L, what is the maximum moment here? W squared by 8. This is a rule that cannot be broken. No matter what software you use, what analysis you use, what system you use, how many load transfer things happen, whatever happens, WL squared by 8 cannot be changed. So if it is a moment like this sum of these negative and positive moment will still be equal to WL squared by 8. And this is the most important thing that you should remember, this formula. If only one formula which you all remember in engineering you want to remember is WL squared by 8, because this rule is the basis for almost everything. Two formulas actually. WL squared by 8 and PL or PL by 2. Just remember these two formulas. Every structure, ultimately, you can break down into a system of that. So all these moments should, negative and positive, should sum up to be WL squared by 8 in each span. So now the only question is, how much of that will be positive? How much of that will be negative on each side? The whole analysis, purpose of that analysis is only to do that, to find out how much is the negative moment, how much is the positive, because the sum we already know. Now, the interesting thing is that if you add these two together, you will not get WL squared by 8. Correct? You just add it together, you won't. Do you remember fractional addition or forgotten all about that? Third grade, fourth grade, right? So if you add those WL squared by 11 to WL squared by 16, both of them should be WL squared by 16, right? Only then it can be 8, but it's not. So which means that these formulas or these factors given by the code are not compatible with structural basic rules. They are breaking the rule of WL squared by 8. So if you go and analyze the same beam in SAP or ETABS, you will get different moments than that, because that program will make sure that the WL squared by 8 is followed, right? This is the code formulas to calculate the bending moment in a beam or a slab. But if you go and model in ETABS, you will get different moment. The question is, who is right, ETABS or code? Yes, code is right. Okay, fine. So let's stop using ETABS. But ETABS is based on finite element. So what happened here? I want to find out. He says code is right. Please remember, there is a whole reason behind these numbers and two different numbers here and these numbers not matching. The reason number one is that the spans, these formulas are supposed to apply to a range of spans when the spans are not even equal. So this WL squared by 8 for each one of them to be justified is only when all spans are equal. When the spans are not equal, some beams will get more positive moment than others, and then the two spans are longer on each side, some negative moment will be larger and positive. So the variation in the bending moment will happen positive and negative depending upon the length of the adjacent spans. So you cannot satisfy the same rule for all the spans. It can't be satisfied because larger spans will lift up the smaller spans, so then the distribution will change, right? So that's the reason number one. So that's why they say that if you want to use this one, this span L1 and L2 should not be more different than 1.3, something like that, 30% variation. These rules should only apply when the spans are within 30% of variation. You cannot use 5 meter and 10 meter and expect this to work. Okay? That's the reason number one, they have this averaging things there. Second, an important reason is that the load is not always applied to all the spans at the same time fully, or pattern loading. So live load, when you apply live load, even dead load, it may not be equally applied to all the beams at the same time. So some span may have more load, so this has to be increased. Those two are loaded, this will go up. This is loaded, these two are not loaded, this will go down. Right? So the variation in the positive and moment line keeps shifting. The total remains the same for that particular case, but every case the moments will be different. So they are taking what is called the envelope approach. They're taking the mean of those several analyses. They calculated several, they actually got many diagrams. When they developed these formulas, they actually got so many diagrams depending upon, they got this one, they also got this one, they also got this one. They got many diagrams for different variations of load patterns and span ranges. And then they took the mean for each one of them or the maximum for each one of them and put them together. So they are coming from incompatible loading arrangements. That's why you don't see them matching. But they are supposed to cover, ultimately, like what he said, safety, because they are simplified and they're supposed to give you a good answer, even if you didn't cover all your bases. So there is always a reason why the code says something. Intent is always good. They don't explain it properly, and sometimes we don't know when to violate it, right? And when not to believe it. So understanding things behind the code is what we are doing all these courses. That why there is something like that, and when you can choose not to accept it. Okay, so that's about that. And the rest of these things you can just read. Then this is another interesting thing. Estimation of the thickness. H is thickness here. Should be T, but it's H. The code gives you an estimate of the thickness to avoid large deflection. Okay, what is the deflection formula? Okay, that's the deflection formula. So good that you remember those two formulas, deflection and moment. So they're saying that the deflection, to control the deflection, the thickness, which will actually determine E and I will be determined by thickness, should be like this. So they try to limit the thickness of the slab to avoid large deflections for a given span. But this is based on length, which is already in the formula here, and it is based on H, which is the indirect calculation from the E, because E is equal to H cubed B by 12, like we said earlier, right? But the deflection also depends on W, which is not considered in this range. So if your load is double than his load, your deflection will be doubled straight away, right? So this formula would be wrong by 100% or 200% depending upon your load. So what load did they assume? Why the code is telling us that you can estimate the thickness? Because this is very important, because we start our analysis and design by using these rules to estimate the slab thickness and the beam thickness, right? But it does not include the W. So please explain to me why W is not here. Simple answers to this one. Number one, the load, most of the load is coming from the self-weight, which is coming from the thickness directly. So that is automatically included in the assumption, because the dead load is a factor of the thickness and the concrete density, which is universal. So there's no need to think about the dead load. That is part of the calculation already. And you might think, what about the live load? The deflection is primarily from dead load, especially the long-term deflection. Long-term deflection is dependent on creep. Creep only happens for dead load, not for live load. And that creep factor is 2 to 3, 4 times the instantaneous deflection. So that means long-term deflection will be primarily controlled by the self-weight, which is already included in the thickness calculation. So this formula has backward calculated those things and come back from there. So you don't need to worry too much about that. Yes, of course, live load deflection will be there, but they're short-term and they recover mostly. Okay? So code has a logic, but you need to understand why it is like that. It seems to be missing something, but it's not. It's indirectly there, and there's a reason for not doing that. Number one, long-term deflection. Number two, self-weight, already part of the T, the factor. Okay, So that explains that. And these two together we use as a design basis. We get the thickness from here, estimate the thickness, beam depth from here, and we calculate the moment from here, and you can do the quick design. Okay, one-way slab done. Two-way slab is another animal altogether, because now the load is going to be transferred into two directions simultaneously. So now you cannot use those factors that I saw earlier. Some other factors have to come in, right? So there are many methods people use: elastic analysis, moment coefficient, strip method, yield line, and finite element. So when we were studying, we only had real access to something like this one, moment coefficient. The others could be used, but very time consuming. I would spend my whole day in one slab and will not get enough money to do that. So we use moment coefficient. And moment coefficient is similar to the coefficient that I show you earlier, but now in each direction, coefficients are different. Long direction, short direction, there's a table depending on that. So you get those coefficients and you calculate the moment in both directions and you design. And that's how we did slabs a long time ago, with the assumption that all slabs are supported on rigid beams or rigid walls and the beams are not deflecting. Only then those coefficients can work. So two inaccuracies or lack of knowledge or lack of understanding come together. One is the load distribution coefficient, and second, assumption that the beams are supports. But we had nothing else to work with at that time, because these things, yield line was there, direct analysis was impossible, finite element wasn't there. Okay. And then we also got these formulas for two-way slab to calculate the thickness, because one-way slab is only one span, so it's easy. Now you have a two-way slab system. You have basically a slab which is like this. So there is Lx and there is Ly or whatever. And then how do you calculate the thickness now? So now these longer formulas start. This is the formula from ACI came in. And so B is the ratio between the slabs, two lengths, and that is the thickness. Interestingly, Fy came into the equation of the thickness. That's another interesting point of discussion. What is Fy doing in thickness estimation? Every class I offer, whoever answers this question, I will invite them for lunch. Nobody has gotten the lunch so far. Let's try again. What is Fy doing in thickness calculation, and why is it at the upper side of the thickness? So higher the Fy, the thicker the slab you should use. That's the second interesting observation. First of all, Fy is there, which is the steel reinforcement, right? Secondly, the higher the strength of the steel, the more thickness you need. Okay, this is very important to note, that why did the code decide to, so please watch this one now. So this is, let's say, moment, what's happening? Moment, and then this is, I'm using some steel Fy1, which is low strength. This is high strength steel, Fy2 equal to 400, and this is 200 megapascal. For the same moment, for the same thickness, this one will give me more reinforcement or less reinforcement? More reinforcement, right? Because low strength steel, in the calculation, it should give me more. So I will get more AST here. So I will get area of steel more here, correct? For the same moment, for the same thickness, I will get a smaller reinforcement here, correct? Deflection is a function of stiffness, equivalent stiffness, transformed stiffness. So in this case, because both steel have the same E, modulus and elasticity of both the steel is the same. So modular ratio will be the same. So this steel multiplied by 10, assuming modular ratio is 10, and same steel multiplied by 10, this one will give me smaller stiffness, this one will give me more stiffness. So which means that for using a low strength steel, I put more steel, I get better stiffness, so I can reduce the thickness. That's the logic behind it. If I use high strength steel, I will be putting in less steel and I will be getting lesser stiffness, so I need to compensate by increasing the thickness, which will further reduce the reinforcement, by the way. Okay, so so everything in the code, every equation, every factor has a reason to be there. And we should try to understand as much as we can, not blindly use those equations, especially the one that make no sense immediately. Like when I saw this equation first time, I said, what is this? I understand everything, but I don't understand why Fy is here. Then you start to think and then you dig out and then that's the reason. So that's the whole thing. This is a simplified formula that we use, parametered by 180 or 20, because sometimes that's complicated. So for two-way slabs, you can estimate the thickness, and estimating thickness for two-way slab is very important because you need to start with that, and dead load and everything will depend on that. And it's not easy to calculate the actual stiffness of slabs, two-way slabs, even through SAP or ETABS. And the simple reason is that they calculate elastic stiffness and elastic deflection. We are looking for long-term inelastic deflection in the slab, which SAP will not give. SAFE will give if you put the reinforcement back and if you do all the moment curvature. You remember moment curvature, right? You can use moment curvature to calculate stiffness. So SAFE can do that. It can go back and calculate moment curvature of the slab and then use that moment curvature to calculate the stiffness and calculate the more reliable deflection, including the long-term effects. So it's a longer procedure. Anyway, so that's and then in continuity in the slab, the other problem is continuity, by the way, this equation did not consider continuity. It is assuming that the slab is not continuous. But here, in any given situation, there are 9 cases of possible continuity of the slab. Each continuity case will change the moment and this deflection. If you have side spans, this span will lift up, obviously. Continuous beams have smaller deflection than the simply supported. We all know that. So continuous slabs will have smaller deflection. So this will have most deflection. This one will have least deflection. Much different. But the codes didn't care about that because they're talking about flat slab systems where beams are not acting, they're not supports. So this is the support mechanism. If you have supports everywhere, then it works like that. And this is what we used to do. And there were coefficients by British code which gave you 6 moments in this one. Moment here, moment here, moment here, moment here, negative moment, and also gave you positive moment here and positive moment here. So you got 6 coefficients and 6 bending moment for each slab, depending upon the ratio. There was a single nice, beautiful table by the British code with the ratio of the slab, aspect ratio, and continuity on one side, 9 columns here, you here, vector there, you are done. Slab's design is finished. So when I saw that table, my first reaction was, I must write a program to make it easier. Who will carry this book all the time? So at that time, I wrote my first two-way slab design program, and then just programmed that table to interpolate for the condition. So my engineers in my office will use that program, they will enter, and then we had a printer, the printer would come out with the bending moments and this reinforcement, and we had the slab design program. So we will just use that for all the project. And most engineers didn't have anything like that. So one day I came to my office on weekend and I saw one of my engineers printing, and he had this whole, the paper used to come in boxes, the computer box. I don't know if you've seen that paper, the box with the roller. So he had printed about 400 or 500 pages of that. He printing, finished all the printer ink, dot matrix, took the whole day. And I said, what is this? Because he was planning to leave the job, and the next job didn't have a computer. So he thought, I will print every possible combination of slab thickness and ratio and continuity, and redesign it 300 slabs and take it with me as my handbook. So when I get a project, I will just go through, find the correct slab and get the reinforcement. So he bound that into a book like this big, and he had that whole design of all possible continuities and spans every meter, and then 300 or something slabs. And that was his design office, so to speak. So that is what we did in gear. And this is just to show you that those 9 cases exist in a slab like this, and you can run analysis in ETAPS now, get the same thing from there, and then you get finally these reinforcements. And so then we move on to what the code did. SCI never really followed that, really believed that idea of the coefficients. They always had different way of looking at the slab design. And this is what I wanted to present. But let me start. So basically, for ACI, they said that let's design a floor slab system which is not on walls. We assume that it is not on walls. We assume that it is on beams or no beams. And then if the beam becomes big enough to be a wall, so be it. So they didn't come from the wall to this way, but they went from no support to wall through stiffness ratio concept. Okay? And that's how the system in ACI slab system was developed, which is quite good. It is still very good after 40, 50, 60 years, 40 years, still going very well. So this is the slab with beams and one-way slab on that. This is a flat slab with drop panels and column capitals. So this is the term 5 comes in now. As I told you, stiffness ratio. So now we see that in the formula by ACI. Watch this one. So it says that if the ratio of the stiffness, and now they included the proportion of the long to short side, everything combined together, they said that if this is less than 5 or greater than 0.25, depending upon how you measure L1, L2, then it's a flat slab system, which means the slab and beams are acting together. And if it is a greater than 5, then it is a beam and slab system where beams are carrying the slab. Here, beams are just part of the slab. So all systems in which the stiffness ratio is between this range are treated the same way. Whether they have the beams or they don't have the beams, same way. And if it is more than that, then you say, okay, fine. Now this is the wall. You can go ahead and do whatever you like, coefficient method or whatever. Now we are not responsible for our method. So this method, so it does not handle beam and slab one way or one way, joist, beam girder, slab, and anything which is 2-step transfer, it doesn't handle. But it handles all direct transfer in one unified method. So flat slab, flat plate. This is a screen capture from Gear program. So when I came to AIT, we developed this software called Gear. It has 30 programs inside for everything from simple triangle calculation to foundation design to flat slab, flat column design, beam design. Everything that engineer needs is in that program. 30 small programs combined together into one system called Gear. It's like a gear when you go for running or for hiking, you carry everything with you. So it's like that. So the program is now no longer used. It was stopped a while ago and CSI bought it. So now it belongs to CSI, but we developed in AIT. So that is a screen capture from there where you can design all these kind of slabs in that program, that module for flat slab. So this one, flat plate. This is the flat slab with drop panels. And this is the flat slab with column capitals. And this is the column capital plus drop panels. And that is the waffle slab, as I mentioned to you. And this is the beam slab. Okay. All these systems that you saw just now, nicely, beautifully done in Revit, belong to the same category of flat slab system or floor slab system. And they are all designed in the same way. There is no distinction between their analysis design procedure. Okay. And that's what I want to discuss next time.